Hello and welcome back again to the Royal Institution. Now the theme of these lectures is handedness, chirality. And we've looked at the chirality of man, and we've looked at the chirality of the artifacts that he has made, and we've looked at the chirality, the handedness of the biological environment that surrounds him on the surface of the globe. And we've also had the suggestion that all these matters are in fact molecular. They're matters of chemistry, and chemistry is the science of molecules. We've suggested that all of these matters are under chemical control. And so it's time that we went into the land of the molecules. We've got to go below the surface of the objects that surround us and examine them to see what they consist of and how they're made up. Now, 2 points. First of all, do remember that everything that confronts us is chemical. You are chemical. I'm a chemical. That's a chemical. This desk is chemical. Chemical is used these days as though it were a dirty word, a term of abuse, but it is the stuff of what we are made. And we must concentrate, therefore, on a few basic points. So let's start off with ourselves. Let's just start off right at the basics and start off with ourselves. What are we made of? Well, we're made of this, as a matter of fact. What we've got here is a human being. It's a human being in kit form. Let me just take you through it. The first point is, and I'm sorry to be so unromantic, that a 70-kilogram man, like me, consists, first of all, of 50 litres of water. I know that's a bit of a disappointment, and some of us are wetter than others, but you're basically just about 50 litres wet. And then we have fat. We've got 10 kilograms of fat, and here it is. Now, interestingly, that's for a male. That's a 70-kilogram male. If you're female, then the amount of water that you'll have is actually less, but the amount of fat that you'll have is more. I just leave that little point with you. You can make of that what you like. Okay, now, the next thing is protein. So here's your protein, okay? And that makes up your muscles and your hair and your nails and the magic catalysts of your body, which are the enzymes. And we're coming to those. And then we'll come to your skeleton. And that's made of calcium phosphate. What we've got here is actually bone meal, very good for growing roses. That's your bone meal. And here's a little bit of romantic chemistry for you. This consists of calcium phosphate. And the calcium here, the calcium in your bones, came from an exploding supernova before the sun was lit. Think of that. And let's look at one or two other things that we've got. First of all, we've got sodium and potassium. These are the reactive elements. that have to be kept tied up here in sealed tubes. But in your body, they're a very important part of your functioning. And then we have sulfur, the most beautiful and gentle and versatile of the elements. And then we've got a little bit of iron in our souls. Some of us have more than others. Television producers tend to be of this sort. They have more iron in their souls than others. And here we have about 5 grams of iron in our bodies. So that's what we consist of. That's a human body. Now it's important to think of what that human body is made of. What's it made of? And how are we to think about this matter? Well, if we go to the 18th century, that was really when proper studies of the composition of matter started. Because we have here a portrait of Antoine Laurent Lavoisier, the father of chemistry. Now, Lavoisier was an unlucky chap because he fell foul of the French revolutionaries, and in 1794 they beheaded him. So watch out, okay? They beheaded him. And Anne, his wife, then married Count Rumford. And Count Rumford was the founder of the Royal Institution. Now, what Lavoisier did, and this is really how he founded chemistry, he said, I'm going to measure the amounts of things of which familiar objects, like, say, for example, sugar, are composed by burning it and collecting the results of the combustion in my apparatus. This flame is just a little bit shy. It's nothing really, just needs to get a little bit of momentum, but it's going. And so Lavoisier would have collected the products of combustion, and that would tell him about the composition of matter. And the important thing about this sort of measurement was that it changed the status of chemical investigations. Up to this time, alchemy ruled. Alchemy, the attempt to change base metals like this block of lead into gold. That was the attempt. And we just happened, just so that you could see a block of gold, we just happened to have borrowed a little block of gold here from the Bank of England. Now think of the density of this material. That is a kilogram of gold. Think what a kilogram. That's a kilogram of gold. Now before the block of gold goes away again, because we're only allowed to have it for a very short time, let me just make the point that a block of gold like that is made up of atoms. It's atoms of gold hanging together. That's the nature of metals. And so that allows us to think, what about the lifestyles of atoms? How do atoms behave, these uncuttable little bits? Well, let's just think about that. First of all, atoms can be singles, just go about on their own. Now, these are not very common. But if you take this lecture theatre, it's full of air. And air is about 1% of what we call the inert gases. These are gases like helium and neon and argon. And they're familiar in such things as neon signs, of course. But they go about on their own. They're too idle to get together. And in fact, the very word argon means the lazy one. They don't want to combine, they can't be bothered. I'm quite happy on my own. That's the inert gases. But the atoms of a metal, like gold. They just hang together. Hang together loosely, and they're quite chummy, but they're not tightly tied together. But the most common type of interaction between atoms, attachment between atoms, is by what we call a chemical bond. So if we take a simple molecule like this, you can see that that is made of a big atom and two smaller atoms bonded together. It's all very well to have balls like this, but how large are atoms really when we think of this uncuttable business? How large are they? Well, let's see if we can give you a feel of this. Let us take a familiar material. We've already seen the lump of sugar burning. Let's take a familiar material. Granulated sugar. If I spread it there, what we've done, of course, is to spread out granulated sugar. But it's just to put the size of a grain of sugar in your mind. Right? So keep in mind the size of a grain of sugar, which is about 1 millimeter. That's actually quite a big grain of sugar. And here it is again. Of course, we've magnified it, so that's the size of a grain of sugar, 1 millimeter high. Now, what I want you to compare is the height of that grain of sugar with the height of Mount Everest, which is 10,000 meters high. And that comparison, grain of sugar to Mount Everest, is the same as an atom to a grain of sugar. Now let me, because this is such an important matter, I just want to put it firmly in your mind with one more example. Let's take a marble. Marble, familiar object. It is 1 centimeter in diameter. Now, if you want to get an idea of the size of an atom by comparison with that, let's compare that with a distance. Its diameter of 1 centimeter. If we go out onto the M1, if there's not a traffic jam, onto the M1, put it down on the M1, presumably in the fast lane, that would cause the maximum disruption, and then go to Rugby, that is the comparison of the distance between the diameter of that marble and the size of an atom. Okay, so they're very, very tiny. Okay, now what about molecules then? Supposing when we put atoms together into molecules, as we did here, then what about the numbers? Well, let's do some chemistry. It's pretty simple chemistry, but it's chemistry, and that's important. Here we've got some water, and I'm going to pour out, if my hand is steady enough, not bad considering. Do you agree with that? That's about 18 milliliters of water. 18 milliliters. So we could then ask ourselves the question, how many molecules of water in 18 milliliters of water? And I need an assistant for that. Can I have a volunteer? Oh, you volunteered. Thank you very much. Come straight down. What's your name?
Neil Humble.
Neil Hamble.
Humble.
Humble, right. Okay, now I'll tell you what I want you to do, Neil. Will you go to that end? That end there. Do you see this board? What we're going to do is lift this board. This is actually a measuring device, okay? Lift it when I give you the go, okay? Right, are you ready? It's quite heavy. Up. All right, hand underneath. On the edge. Okay, ready? It starts with 602. Keep pulling. Keep pulling. Keep pulling. That's right, keep pulling. Try not to poke it into him. That's very good. Okay, well done. That's good. We nearly knocked your block off, didn't we? Jolly good. Thank you very much for coming. So that's the number of molecules. Now, we've got to see one or two little things on the bench, so I wonder if I could have a hand just to lift that down again. Could I? Thank you very much. Okay, it's fairly heavy. Down we go. Very good. So that'll remind you of the numbers that we're dealing with here. Very good. Thank you. So we're dealing then, at this molecular level, with the sizes of atoms and molecules and their numbers. Now, it's actually easier to deal with these matters if we have pure materials. Now, what do we mean by a pure material? Well, the best way of looking at that is simply to have a familiar illustration. Bryson, please bring me in my breakfast tray. Thank you very much. Thank you. You just put it down there. That's fine. Thank you. So let us look round this tray at what things are mixtures. So if we take cornflakes, that's a mixture of all sorts of things. Carbohydrates and salts and everything else. The orange juice is a mixture. The tea and the teapot is a mixture of molecules. The cup of coffee, teapot and coffee, that can't be right. Anyway, no matter. That's the cup of coffee is a mixture. But there are two pure things on this breakfast tray. Those are our glass of water and our bowl of sugar. And probably these days, with the privatization of water, it's actually the sugar is probably purer than the water. But that's another matter. No. Now remember that we are 87% water. 87% of our body weight is this stuff. Okay. And there's its molecule. 2 hydrogen atoms and an oxygen atom. H2O. That's a water molecule. And without water, our lives could not exist. Okay? We wouldn't be here if it weren't for water. We're a water-based life. And the other thing that we wouldn't be here without is sugar. Okay? Sugar is the energy carrier. We've got sugar being carried around in our blood at this very moment, allowing us to move. That's also, it's the energy carrier of life. And let's just think a little bit about the nature of the structure of a molecule of this. What we've got here, you see, is this molecule made out of hydrogen and oxygen. And hydrogen just loves oxygen. This chemical bonding here between the hydrogen atom and the oxygen atom is very strong. And we call this a hydrogen-oxygen grouping. Okay? Vital for life. And I want to plant in your minds, because we're going to come back to it in a moment, is the fact that this is a sticky molecule, and it's sticky, the water molecule is sticky by virtue of the fact that it's got a hydrogen-oxygen grouping. We'll come back to that, but just think of sticky. Now, let us compare the structure of this little molecule with the structure of glucose, which I've just mentioned, and here it is. Now, thank you very much. And what we're seeing here, of course, is a much more complicated molecule. It's much larger than water, but it's got structures in common here. Parts of this molecule are very much in common with the water molecule, And I particularly want you to focus on this part, because you see the red oxygen and the hydrogen. Now, what about the arrangement of an atom? It's all very well to look at a complicated molecule like this with lots of bits and atoms all over the place. But how do we know that these atoms are arranged in the way that we see them here? Because this is a faithful representation of the molecule. Now, there are many methods of knowing about how atoms in molecules are arranged. It's one of the most important aspects of chemistry because we're doing it all the time. And one of the ways in which we find out about the arrangement of atoms in molecules is to use light. And we're going to use light in two ways in this lecture. So let me just give you a little retread about light. It's something it's very familiar to us. The light comes streaming through the windows of the Royal Institution, and if Bryson will light us light, then we can just look at that. We're going to get a nice, brilliant light. Yes, good. And what we have, you can see here on the screen, that what we've got is a nice, sharply focused little plane of light. Fine. But you already know perfectly well that light is not just white. You know that already. You know that light has many components, colors, and these can be split apart with a prism. This was discovered by one of the giants of science, Newton, in his cottage out in Norfolk. And what he did was to take a prism. He took a prism of this sort, which you can just see here, and he put that in the light path. And if I ask Bryson to do exactly the same, here we are. What happens is that the white light is spread into its components. You know the mnemonic. Violets in boxes give you odors rare. That's how to remember the order of the colors in the rainbow. But beyond the red part of the spectrum is a part known as infrared radiation, and that's what we're going to look at. Now we've got an instrument which is common in laboratories. It's a very nice, neat little instrument. Well done, and here it is. Now what it does is to produce infrared radiation. It's called an infrared spectrometer, and the infrared radiation is generated in this part of the instrument. So the infrared light shines through the sample and into the detector, which is here. Here we've got a sample chamber. We're going to put that sample in there in a moment. Then the radiation will come through and be detected. And then what it's going to do is really to draw the fingerprint of the molecule of the sample that we're putting into the spectrometer. So let's just do that. Here we go. That's now in the sample chamber. If I close the lid, press the right buttons, what is going to come out is a picture of that molecule. And what is happening here is that the radiation is coming through the sample, and part of it is being absorbed. It's being taken up by the molecules that we've put in, and here's the picture. But here, there's no absorption at this part of the spectrum. There's no absorption of the radiation, and then suddenly it takes it up in this lovely big curve here, and then it's back to no absorption. And that part of this picture tells us that there are hydrogen, oxygen groupings in this molecule. But this technique can be used for taking the fingerprints of molecules. So in a sense, we can treat molecules just like criminals. We take their fingerprints, put them on the file. We can do exactly the same with molecules. We can take their infrared fingerprints. And that's very important in assigning the structures of these materials. Thank you very much, Bryson. Now, I gave you a throwaway line, which I hope you've been thinking, that can't be right. I said that water was sticky. And I bet you didn't believe me. I bet you didn't. But I hope to convince you that that's true. Now, a very important property of molecules, these things which are made from atoms, is that if you have molecules of about the same size, then they have very similar properties. Unless, if you're making a comparison, one of them happens to be sticky. So let's compare two molecules together and see what their difference in stickiness is. Let's take a molecule which is very familiar, and this is the molecule of methane. Methane, that's its shape. Now, you're familiar with both of these molecules. When you go home and have a bath, you'll turn, as I hope you will, you'll turn on the tap and out will come water. If you turn on the gas stove, out will come methane, because of course that's the main constituent of natural gas. Now, what do we mean by stickiness anyway? And what we mean by stickiness is this. Molecules collect together, and if they're going to be separated, unstuck, they will escape from, for example, the liquid. We can see that here with water. And if we put enough energy into water, and Bryson's going to start energizing this flask of water, that will make water molecules escape from the water and into the space above. Right? Now, if this is happening very easily, what we expect the molecules to do is to escape from the liquid and into the gas and perhaps blow up this balloon. Right? Well, it's slow, and in any case, the warmth of the flame is expanding the gas above, but that balloon's not doing much. Let's just compare that with the stickiness of methane. These molecules of water are being unstuck here, but when we come to methane, Bryson has liquefied some methane. Here it is in the tube. You can see it sloshing about in the bottom of that tube, which is covered with frost to keep it cold. It's frosted because it is so cold. But he's actually unsticking liquid methane by warming it up in cold water. A nice, dramatic little experiment. It's always nice in the Royal Institution to have very carefully planned experiments. You see, that sort of thing, it can't just be done, by accident. Now, what's the difference between these two? In this flask, the boiling is happening. The unsticking is happening at a temperature of 100 degrees centigrade. But methane becomes unstuck at minus 167 degrees centigrade. And so I hope I've convinced you that there's a stickiness difference between those two molecules. Now, you remember the glucose molecule here, and I pointed out the fact that we had a big red oxygen atom and a little hydrogen atom beside it. The two molecules had that in common. So this is the way that your mind should be thinking. He's saying that's sticky, and I sort of half believe that experiment. It's not bad, but it's okay. But if that's true, glucose should be sticky as well. That's what you should be saying. Well, let us try and illustrate for you the stickiness of glucose. So for the purposes of this demonstration, all I need is a roll of brown paper covered with glucose glue, and I need a volunteer. Thank you very much. Will you come down, please? What's your name?
Julian.
Julian, right. Julian. What do you weigh, Julian?
I weigh 40 kilograms.
40 kilograms. Right, fine. Would you like to show this sticky paper to the audience? Right, look at that. Would you like to tear off a bit? Show it to the audience that it's an ordinary piece of sticky paper. Positively no deception. Use it for doing up parcels and things. Would you like just to tear it to show how weak it is? Poof. Right, jolly good. Thank you very much. Now, what we're going to do, and we're going to use the stick, and so we must let Bryson stick what we've got. Let me just explain the structure of this. We're going to use a rope, right, which is stuck together. So we've got a piece of this same paper there, and there, and there, and there. Got it? Bryson is going to keep licking all these surfaces, and then we're going to stick them together. And we must let him get on with that, because he'll need a second or two to dry it. Yes, he's going to get on with it, whatever I say. Very good. Shall I hold that bit while you... Are you all right, Bryson? That's good. I'll hold that. Right. You've got plenty of stick. We didn't volunteer other people, because it can actually take a rather... You know, you need plenty of spit. And that's good. All right. Now let's just see what we're going to do. All right, Bryson's got that good and stuck up. Would you like to get into the safety harness? Now, I'd just say a little bit, because we're very, very safety conscious in the Royal Institution. Now, this piece of equipment, all right, is going to haul up. You see, that rope is going to consist just of sticky brown paper, all right? And so to make sure that nobody gets injured, we must have a safety rope, and we'll show you that in a moment. But what we're going to do is putting him in his harness. This is training for helicopter rescues. That's good. He's all held up like that. That's very good. Now, what we've got here, put that in the clip as well. That's good. That's fine. Are we all secure? Now, I don't want you to be distracted by it. This is simply a safety rope. It has no function in this experiment at all. It's just in case the glue on our brown paper, which is glucose, that glue is glucose. Just in case glucose isn't as strong as we expect, that is simply a safety device, because we don't like dropping young people on the floor of the Royal Institute. Right, okay, fine. So that's pure safety. Now, let us take the strain. Are we ready? Notice we're straining that one because that's just loose. Okay, now, what we want to do, can we lift you just a few inches off the floor? That's it, look, right? So it's holding it so far, right? Exciting, isn't it? Right, now can we go a foot off, Bryson? He has to work very, that's fine. Look at that. He's clear of the floor. Okay, the tension is mounting, also on the sticky paper. So will you pull up, right up? Look, there he goes, higher. Now, we don't want to take him all the way up, because we do have a lecture to get on with here. But he's able then. I hope you're convinced. What more does it take? Could we let him down again, Bryson? Thank you very much indeed. That's good. Now that is just the interaction, the attraction of one hydrogen-oxygen grouping with another. It's holding that. But we can undo that. It's just paper. That's all it is. It's just paper. It's nothing more than that. Okay? That's molecules. That is not magic. That's molecules. Now we're going to use light in another way. I told you that we're going to see two different light arrangements. And we've seen infrared light. Now we're going to use yellow light. You'll see the light going on in a moment, but I need to explain the nature of light. So just come along with me. This is something that I need to explain with models, first of all, because otherwise I think you'll find it difficult to take in from the equipment. So let me just remind you of the nature of light. Here we have a Royal Institution ray of light, okay? And it goes up and down like that, as you see. And it will shine through things, of course, which is extremely familiar. But this ordinary light that we see coming through windows and so on is chaotic. It wriggles in every direction. But for the purposes of the experiment that we're going to do for you now, we want light which will wriggle only in one direction. That direction. In the direction now, that plane. All right, that plane. And that is what we call plane polarized light. Now we can make plane polarized light in the following way. We take a chaotic ray of light and we put it through a special prism. We can call that a gate. It's a special prism, but we can regard it as though we're going through this gate. And if we have another gate through which this ray of light can pass, like that, that's fine. This plane polarized ray of light can go through this one, and it can go through that one. Fine. Now, if, however, we turn that gate at right angles like that, then our ray of light can't get through that gate. Can't get through. It slipped. It can't get through there, and so that one blocks it off. Okay? I was just forcing it a bit too much. Right. Now let's see that in operation in what we call here a polarimeter. Notice now that we've got some yellow light and it's shining through this device. Now this is a lovely scientific antique. This has been in these laboratories for about 130 years. So this is not a modern piece of equipment. It's an antique which is lovely to have working for us again. Okay, so it's a 130-year-old instrument, and what I want you to see is that the light is shining through the polarimeter, and what I want to do is the equivalent of closing the gate. I'm closing the second gate just by moving that like that. That closes the gate. This instrument, or one very like it, figured in the greatest chemical realization of the 19th century. And that realization involved a bottle of wine and a brash young man in France by the name of Louis Pasteur. Let me tell you the story. It was already very well known that if we take a bottle of wine, a good quality wine, such as they have in the Royal Institution, and you pull the cork, what one finds is a cork which is covered with crystals. And these crystals are crystals of tartaric acid. But if we pour some of this wine out, just so we can see the nature of the wine, then another tartaric acid also appears in this wine. Now there's a difference between these two tartaric acids because although they have identical structures determined in just the sort of way that were being used to determine the structures of molecules as we've seen, they had one very important difference. And that is, when these crystals on the cork and settling out in the bottom of the bottle were dissolved in water and placed in the polarimeter, they affected this plane polarized beam of light. But when the acid, the other tartaric acid, separated from the wine, was put into the polarimeter, it had no effect on the plane polarized beam of light. So this was a great mystery. And it was a mystery that senior chemists of the age had been unable to solve. The year was 1847, and they had given up this problem for lost. They had capitulated. But this brash young Frenchman, Louis Pasteur, felt that it was not right to have a mystery such as this pass without an investigation from him. And so he looked at the crystals of the acid which had no effect on the plane polarized light. And here they are. When he looked at those crystals under the microscope, he was able to see a subtle difference between them. And that was that they had facets which were respectively right-handed and left-handed. And that put into Pasteur's mind the idea that these might represent different tartaric acids which were related as right and left. And so he took this acid and he examined it under the microscope and he separated it, seeing these crystals and being able to recognize the fact that they were right-handed and left-handed, separated them into two little piles, left and right. And he dissolved them in water and placed them in the polarimeter. And we can now reenact for you this marvelous moment in the history of chemistry. He took the pile on the right and he put it in the polarimeter. And notice what happens. The gates were closed, and now that has opened the gate. If you just close the gate again, Bryson, so we can see, that closes the gate again, and in order to close that gate, Bryson has had to move that round about 30 degrees to the left. Now Pasteur took the second pile of crystals and he dissolved them in water. I should have mentioned that. He dissolved them in water. The gate closed again, but this time now it's opened the gate again. So it's had an effect on plane polarized light. And this time, in order to shut the gate again, watch, Bryson has to rotate it the same amount, the same 30 degrees, but this time in that direction, in the equal and opposite direction. And it's so Pasteur realized at once, first of all, it's nothing to do with the crystals, nothing to do with that because there aren't any crystals in the solution, but that this acid from the wine, which had no effect on plane polarized light, was a mixture of two separate molecules, both of which affected plane polarized light and in equal and opposite directions. And so Pasteur said of these molecules, these two tartaric acids, they're like my hands, my right hand and my left hand. That's how they're related, and they don't match. When I put my hands on top, I have a right thumb and I have a left thumb. And he said this is the relationship between these two tartaric acids. They are like my right and my left hands. And here are the models of these two tartaric acids. Let me just show you that. If we start here, just let me sort of wave you through the molecule. Start here, and as we move out, that is on that side with its hydrogen atom there, but that's on the other side. This is on that side as we move away there. So these are like Pasteur's right and left hands. And these molecules, and the relationship between these two separate molecules, is the most subtle that we can have between any two. And that handedness, these are handed molecules. That's a right-handed molecule, that's a left-handed molecule. As I look at them, it'll be the other way around for you. Okay, that's the right. These are handed molecules. But that's what these lectures are about. They're about handed molecules and their effects. Now, you could be wondering, well, Pasteur could separate these two-handed molecules by fiddling about with tweezers under a microscope. Terrible business, terribly tedious, and actually it's very rare. Pasteur was lucky. It's very rare that, first of all, handed molecules separate from a mixture in two opposite crystalline forms. And he was working in Paris in the winter. You think, what's that got to do with handed molecules? Well, he could only have seen the difference in the handedness below 27 degrees. Above 27 degrees, the crystals don't show their separations. They don't show the different crystalline forms. And if it had been summer, Pasteur could not have made this enormous realization. Now you say, well, it's just luck. Scientists are not keen on luck. What is important is that chance, and this was a matter of chance, favors the prepared mind. So if your minds are prepared, you'll make discoveries. Thank you very much. Can we get rid of those? Thank you. Because we want just to look quickly at another very important matter. The relationship there is obviously very subtle. They're intimately related, those handed versions of the same type of structure. But the separation of handed molecules, that's not just an old-fashioned matter from the last century. It's a day-to-day activity of chemists, particularly in the pharmaceutical industry, where it's very important to be able to make specifically handed molecules. And so we have to be able to separate a mixture of handed molecules, and that process is known as resolution. Now let me just illustrate that for you. We happen to have a handed molecule separating machine. His name is Dr. Bryson Gore. And we're going to do a little experiment. It's actually to show you how we do the separation. And we want Bryson to be just a machine and not the fine, upstanding, intelligent man he is. And so we're going to blindfold him, all right? So he's blindfolded so that he can't see what we're doing. And we're going to turn him into a machine in a minute. But what I need now, hands up, all the left-handers in the audience, first of all. Hands up, lefties. Okay, will you come out, please? Can you manage? You just shuffle your way around there, that's good. And you're a lefty, thank you very much. And I think I had a lefty on this row, didn't I, somewhere? A lefty, yes. Will you come down? Thank you very much. That's good. Now in this experiment, I want you to use your natural hand. Okay, because you're going to shake hands with Bryson in a minute, but I want you to use your natural hand. In other words, your left hand for you three. Now, can I have 3 righties? Very good. Yes, thank you. Will you come? Thank you very much. And will you come? Yes, thank you very much. Why don't you two come? Yes, and blue jersey. Thank you very much. Yes, that's right. Follow us, he says on his jersey. Jolly good. Follow everybody. Now we're going to jumble you up to make sure this is a working experiment, you see. Scientists have to work very hard at making sure the experiments are correct. Would you like just to go in there? Bryson can't see what we're doing anyway, you see, and so it's very important. We've got you reasonably jumbled up. Now, you must all shake hands with Bryson with your natural hand. Okay, so lefties, use your left hand, and righties, use your right hand. Very important. Now we're going to turn Bryson into a machine. Right? There he is. Look at that. See? He is a handed separator, a molecule separator. And he's going to show you how you can separate molecules. Right. Start off. You're a molecule. Just shake hands with Bryson's detector, and he's going to shout out. He's a lefty. Stand over there. Yeah, you can go back to your seat. Thank you very much. Lefty.
Right.
Right.
Left. Right.
That's good. Back to your seats.
Left. Right.
Very good. Thank you very much. We're releasing now, Brian. And this recognition, which is another theme of these lectures, is a matter of handedness. Not merely can we separate molecules, as we saw there, quite reliably, but we shall see that the interactions between them are very important. Now, we've been talking in these lectures, in this lecture in particular, about handedness, the handedness of molecules, but we've knocked off expressions like atoms and so on, really asking you to trust us. And we've been talking about the Greeks and Lavoisier and so on, but I want to show you pictures of atoms. And we've got an instrument here which is capable of revealing to you pictures of atoms. It's very new. There are very few of these instruments in this country, and it's called an atomic force microscope. And what it enables us, as I say, is to take pictures of atoms. Your atom photograph machine. This is what this is. And remember how small atoms are. Remember what a huge number there were and how tiny with regard to Mount Everest. Right. Now, what you do with an atomic force microscope is this. We have a very expert computer operator. Please, will you join us? I was just about to start the spiel, and then I realized I wouldn't be able to work the machine. Can we know your name? Susan. Okay, Susan. Will you sit on the stool there? Thank you very much. And then you can start to operate it for us when I give you the signal. Okay. Right. Now, what you actually do, I'll give you the signal. What you do is you take a sample. Now, the actual, because it needs a little bit of adjustment, we can't do the full experiment in the lecture, but we've got a sample holder here. And we put in a little mica slide. Mica, so that goes in there, and then we shut it again, like that. Fine. Now, what we're seeing already on the screen here is a sort of distant view of this sheet of mica. We're looking down on it from a height. Okay? Now, Susan, will you focus in now to the atomic level? So we want the first picture. So Susan is going to get this first picture for us. Okay? What is happening is that a little silicon needle in this machine is coming down very near the surface, and it's feeling its way about on the surface. And now we've got atoms. Each of these black dots here on this picture is an atom. That's an atom. Now that's right close down near the surface. And if we look at that surface from an angle, 45-degree angle approximately, Susan, will you take us to that picture? Remember what we're doing. We're flying down and looking at that. It's coming up in a minute. That's good. She's very expert, this girl. Wish I could work the computer like that. Here we are. Here's the 45-degree version. Think what we're doing. We're coming in across this molecular atomic plane here. These are all atoms connected together here. So it's a series of molecules. We're coming in here. Here's the molecular plane. And this cliff that we've come to here is only 1 atom high. That's the world's smallest cliff. Susan, thank you very much for coming to help us with that. Thank you. So in this lecture, we've seen of the existence and the nature of handed molecules. And now we should consider the effects of such molecules on us. And that is the topic of tomorrow's lecture.